Esther. Yeah, so I'm Tyler, and I'm going to be talking about Zookeeper versus Raft, stateful distributed coordination with HA and fault tolerance. So first, I'm going to give the outline of the talk. So the first part is what I mean by stateful distributed coordination services. And then I'm going to talk about how we do this in Alexio, which is our sort of journey through high availability and fault tolerance, going from Zookeeper plus an object store to Raft, which we use now. So what do I mean by stateful coordination services? Well, let's look at a couple different examples. So first, of course, we can think of Kubernetes, which is a system for container orchestration, which you can use to sort of build any distributed system. And so the core of Kubernetes is you're going to have your nodes, each running your different containers, each providing their own services or microservices. But what we're interested in talking about today is this control plane, which is the system that it's going to maintain the state of the entire distributed system, which means, so this control plane is going to make sure the correct nodes are running, schedule jobs, basically control the state of the system. And one thing that's important here that we're also going to focus on is sort of this is all backed by a storage here, which is the persistent store, which keeps the state of this control of the system. And that's, in this case, it's a key value store called etcd. So that's an example of Kubernetes, of these stateful coordination services. And then we have something similar in Kafka, which is a distributed event streaming. So in Kafka, you have a bunch of producers producing information and producing streams of information, and consumers who are consuming the streams of information. And Kafka is going to organize the streams of information into different topics so that consumers can subscribe to different topics. And so Kafka itself is going to be broken up into these nodes called brokers, which are going to replicate these streams of data. And again, but what we're interested in here is the distributed coordinator. So in Kafka, this coordinator is going to map the topics to different brokers. It's going to choose which broker is the leader of the topic. It's going to choose it's going to inform the producers where the different topics are located. So again, we have this sort of coordinator sort of running the system. And then we can also think of transactional key value stores. So here, for example, is a Foundation DB, which is a replicated key value store, high availability. And so the core of Foundation DB is made up of the transactional system, which includes your storage layer, your log layer, and these transactional processes who are going to be sequencing and organizing, executing the transactions. But again, here we have what we're focused on is this control plane. And this is going to store, the coordinators are going to store the state of the system, meaning what nodes are being run in this transactional system. And it's going to, these controllers are also going to make sure that if a node within this transactional system fails, it's going to restart it and recover from a failure. So again, we have this control plane that keeps the system running. And we can keep going. So Spanner has zone masters. So Spanner is a globally distributed database by Google. And the core of it is the span servers, which is going to execute the transactions in different zones and store the data. But here they have something called a zone master, which is it's going to sort of keep track of which span server is going to replicate which part of the data. And then we have F1, which is sort of the SQL version of Spanner at Google. And this has another layer of processes executing, and these F1 servers are going to be organizing these SQL transactions to be run over Spanner. But again, we have a master, which is going to coordinate and make sure these slaves are running, and going to coordinate the transactions between the different slaves. And then another example, we have HDFS, which is a distributed file system. So this is your sort of basic file system, which have directories and files. And here the files are going to be replicated on these data nodes. But again, we have a name node here, which is sort of our metadata store, that's going to coordinate where the files are located, on which data nodes, and sort of store the structure of the file system in the metadata. So that's sort of just an overview of what these sort of distributed coordination services are and what they can do. So usually they're doing things like metadata configuration, making sure the cluster is healthy, naming services, choosing leaders for different parts of the system. And so sort of the overall concept of these is they're a small subset of the system, but they need to be really strong, have strong properties, because they're going to make sure our system is running correctly. So they have high availability, fault tolerance, and strong consistency. And so now I'm going to talk about what this means in Alexio and how we have implemented these coordination. So what is Alexio? Alexio is data orchestration for analytics and AI, which is basically sort of a middleware between your compute layer, such as Presto, Spark, MapReduce, and your AI or an AI framework, and your object store below, which is storing your data, such as S3, Google Cloud, Azure, HDFS. And so what Alexio does then is it unifies all these different systems and gives you a single sort of file system that you're able to interact through. So as I said, Alexio is going to give you this middleware working as a file system. So what is the architecture of Alexio? So it's similar to like the HDFS file system. So we have the UFS, which are these object stores that I mentioned before, which is going to store the persistence of your data. And then you have the clients here, which are the Spark or Presto or your AI frameworks that are accessing the data. But now they're going to go through Alexio instead of directly through the object store. So Alexio is going to replicate this file system. And it's made up of two main components: the master, which is going to store the metadata. And this is what we're interested in today. And so it's going to store the metadata, which is the structure of the file system. So which is made up of the inode tree, which basically maps directories and files to inodes, which store the metadata about them. And it coordinates where these files are going to be replicated, which is on the workers. So the workers are going to sort of act as a cache of file data between the UFS and the clients. And the master is going to coordinate all these files and keep the metadata. And within the master, we have a journal. So the journal is basically your log of events of the system. And so that's going to be important for us for ensuring high availability and fault tolerance. So now how is fault tolerance done in Alexio? So as we said before, the workers are sort of this cache layer between the UFS and the clients. They're storing the actual file data, and we can replicate these, and they sort of act as a cache, so we can safely shut them down and restart them and replicate many of them. And the UFS itself is going to have its own high availability and fault tolerant guarantees. So our master, which is storing the metadata and coordinating the workers, is going to be our central point of failure. So we need to make sure this is high availability and fault tolerant. And so within the master, sort of a core of any distributed system is going to be your journal or your log, which is basically tracking this total order set of event changes in your system. So every state change is going to be recorded on this log. For example, creating a file or deleting a file is going to create an event, which is going to be logged as a state change. So that in the case of a failure, all we have to do is replay this log, and we get to our original state. And of course, within the journal, we can take snapshots of the state. And this way, we don't have to replay the log from the beginning. We can start from a snapshot, which allows faster recovery, and it can be smaller than just the entire log. So how do we start this basic fault tolerance of our master? Well, since our journal is our unit of tracking the state of the system, we want to make our journal fault tolerant. So if we have a fault tolerant journal, then if the master process running over this journal crashes, all we have to do is start a new master, replay the journal, and start serving clients. But of course, detecting that the master has failed, starting a new node and replaying the journal takes time. So the system will be unavailable during this time. So our basic high availability means we're going to run multiple masters. But within these masters, we're going to choose one of them to serve the request. And we're going to have secondary masters, which are just going to replicate the state of the primary master. And if the primary master is detected to be failed, then it will take over. So this way we can quickly fall over between masters. So our basic design is we've added this sort of fault tolerant journal at the bottom, and we have multiple masters running over this fault tolerant journal. The primary master is appending entries to the journal as state change is happening, and the secondary masters are reading from the journal to ensure they're up to date, and they'll take over in case of a failure. So with this basic fault tolerance model, how do we need to ensure this is running correctly? So we need to ensure that we have a single primary master running at all times. So we need to be able to elect one of these masters to be running, to be chosen as the primary master, and we need a journal itself to be fault tolerant. And the journal itself needs to agree on a total order of these log entries, so that there's only one entry being appended at a time. And this may require consensus, which is sort of this distributed agreement problem. So now I'm going to talk about how we actually implement this. So first we start with Zookeeper and a UFS journal. So our first problem to solve, we want to ensure a single primary master is running at a time. So we do this using leader election using Zookeeper. So Zookeeper is an open source, sort of highly available server framework for distributed coordination. And it provides a file system-like abstraction built on top of a consensus algorithm. So Zookeeper itself is run on a cluster of nodes. And it's going to give you this sort of interface to a highly availability fault tolerant abstraction that's like a file system. So one of the things Zookeeper provides is called a Zookeeper curator leader election recipe. So this simply means that each of our masters in our system can subscribe to Zookeeper for this leader election recipe, and the recipe will select at least one of the nodes, or exactly one of the nodes to be the leader. And it will detect if the leader is fails because it will time out. So if it's fails or it's unavailable to be reached, then the recipe will elect a new leader. So that solves our first problem of choosing a single primary master to be the leader. And then our journal itself, we need high availability and fault tolerant guarantees for this. So in our case, since we have our object store below that has its own availability guarantees, we'll store our journal to the existing object store, which would be, in most cases, it would be HDFS. So I guess the first thing to think about this solution is that, but does leader election by itself solve all our problems? And the thing is not quite. So when we run leader election on Zookeeper, it will do its best to ensure only a single node is chosen as leader at a time, but there's still asynchrony in the system. And because of maybe network issues or scheduling issues within the processes, within the masters, two of them may believe they're leader at the same time. And during this time, we may have multiple nodes trying to write to the journal concurrently. So I think it's important to note that leader election is sufficient to provide consensus. So just deciding on this total order of log, but it's not a consensus protocol itself. So we need to provide some additional mechanism to ensure our journal is correct. Since in our case, we're using the UFS here, we'll use consistency guarantees in the UFS to ensure only a single writer to the journal. And this is done by using a sort of a state transition protocol when an Alexio master is being elected as leader or stepping down from leader. So they'll all start as secondary masters. They'll join this leader election. And when they're elected leader, they'll then perform this primary master protocol, which means accessing the UFS and ensuring that they're the only single writer. So in most cases, this means taking a lock on the file in the UFS. And this has some particularities depending on the UFS being used, but the basic idea is that we're using the guarantees of the UFS to ensure that if multiple of these leaders try to write to the same journal file at the same time, only one of them will succeed. And our leader election is basically helping to minimize this case to ensure that our system is running smoothly most of the time. So how does this architecture turn out? So we have our, same as before, we have our UFS underneath. We have the clients accessing the data through Alexio. And the clients are communicating with the primary master, which is then appending, which has been elected by Zookeeper as a leader, which is appending, as it's making state changes, it's appending entries to the journal. And then the secondary master are reading from the journal on the UFS as the system goes on. So Of course, this isn't an optimal solution. It's relying on multiple systems. And they're each having their own fault tolerance and availability guarantees. So it becomes more complicated. And even writing to our journal is difficult because different UFS has different consistency models and performance. So it might not be efficient for log. So now I'm going to talk about how this implementation evolved to using Raft as our journal for ensuring our masters are highly availability and fault tolerant. So I think the first thing we have to think about is we have to go back to our journal itself. And we have to think of it as a state machine. So what is a state machine? It's basically you have input commands and you have a program running the state transitions. So in the case of our journal, it's just simply the command is append, which appends a journal entry to the end of the journal, which is the state transition. So the deterministic state transition, once it receives this command to append, it's going to execute it and apply the entry to the journal. And of course, we can also query the journal. So just a very basic sort of state machine, journal as our log as a state machine. So then where does Raft come in? So with Raft, we can basically turn any deterministic state machine into something that is highly available and fault tolerant. So basically we plug our state machine into Raft, and then it will ensure that this state machine itself is highly available and fault tolerant. And it does this by replicating the state machine. And this is broken down into several components. So first is the consensus component of Raft, which means you have multiple machines running Raft, and they're each going to agree on a single total order of commands. So as your client is issuing commands, the consensus is going to agree on a single order of commands. And then these commands are going to be logged at each node, which is going to ensure that when a node fails, it can recover from the log, and it can send log entries to other nodes in case their log has failed. And then below this is just our state machine. So once a command has been agreed upon, it's going to be sent to the state machine, which is going to execute the command. So the command is going to be executed. Since the state machine is replicated on each node, the command is going to be executed on each node in the same order. And since we've implemented a deterministic state machine, all state machines are going to be in the same state, given the same, when they're at the same index in the log. So basically Raft turns our state machine into something highly available and fault tolerant, but to the client, our state machine is just, we're just sending commands and we're reading from the state of the state machine. So to the client, it just looks like it's being executed as a single state machine. We don't have to know about how it's being replicated and things like that. So back to our journal. Well, since we can implement any state machine, we don't actually need to have our journal as this log as we had before. We can use a higher level abstraction that we can use as our state of our metadata. So in this case, right, what our masters are doing is they're tracking the file system metadata, which is this inode tree, and it's mapping the inodes to the workers, and sort of coordinating which workers are going to replicate which files. So now, instead of using a log as a state machine, our file system metadata is actually more easily represented as a key value store. So our commands are just going to be writes to the key value store, removes, and reads. And so we have a sort of our own custom sort of table as this state machine, which is going to have our different inode IDs, our inode metadata, and sort of worker locations where the data is located. So now we have Raft replicating our metadata as this key value store. And we don't have to worry about this journal as a log anymore. So what happens then is that our masters are co-located with these Raft nodes, which is storing the state of our metadata. And now Raft is ensuring that this key value store is high availability and fault tolerant. So we just need to run our master processes alongside this Raft replicated state machine. So the masters then are just, in some sense, stateless processes running on top of this, running on this node that's accessing the state machine replicated by Raft. And so we implement our own sort of key value store using RocksDB as our state machine. And the reason why we do RocksDB, of course, is we don't want sometimes our metadata will go larger than memory, so we want to store it on disk. And RocksDB gives us the ability to do this as an efficient key value store, which is made up of a log structured merge tree, which gives us efficient inserts. And our inode store or inode tree and worker information is mapped as this key value store in RocksDB. And then our state machine also, we build an additional cache in memory to ensure reads are fast. And RocksDB also gives us efficient snapshots. So when Raft needs to take a snapshot of the log, it's fast, and our system can recover quickly. So now we look at this architecture that we have now, and it's much simpler. We have our clients and our UFSs accessing our master, and within the master, we have our Raft running. At each replica of Raft, we have our Alexio master process running, which is serving these client requests, but its state is going to be stored in this key value store replicated by Raft. And again, we want to so again, we want to have a single primary master running at a time. So Raft is going to, Raft actually has a leader election built in. So we use the Raft leader to serve the client requests. And when the Raft leader changes, we also fail over to the change in the Raft leader that our clients are then forwarded to. So the architecture becomes much simpler. So our advantages are simplicity. With Raft, we're just co-locating our masters with Raft. And our journal becomes, instead of this log we have to replicate, it's a key value store. So it's sort of a higher level abstraction that we can work with in our own state machine. And we're able to sort of tune our own performance that we need within the state machine. So we are able to use RocksDB, and we're able to put some of the state in memory and some on disk, and we can co-locate the Alexio master processes with the Raft journal processes. And then so now that we've seen how this is done in Alexio, so back to the early examples, it actually has a lot of similarities. Kubernetes, what we saw before is our control plane is backed by its state is stored in etcd, which is a key value store that is also run on Raft. And you have your processes, your control plane processes storing state through this etcd Raft implementation. And the Kafka coordinator is run using Zookeeper. So Kafka uses Zookeeper for a lot more than leader election. It also stores it uses the Zookeeper abstraction to sort of map the different topics to different broker nodes. And Foundation DB, the coordinators are running Paxos, and they're storing their information on disk, and they're responsible for sort of starting and stopping the other coordinator nodes in the cluster and making sure things are running correctly. So generally what we have is a Paxos-based consensus algorithm running replicated state machine, normally as some sort of simple data store with some custom application logic running on top. Yeah, so now that's the talk, and if there's questions.
Yeah, we'll get a few questions. I want to ask one first. So you talk about using Raft to replicate the different state, but one of it, when you talk the first design, you using Zookeeper. One of the key function the Zookeeper is the leader selection. But with your Raft state, how do you select leader then? Which one is a primary?
Right. So Raft itself is going to be run a sort of a Paxos-based consensus algorithm. And this is going to be so Raft actually, part of the consensus is that it elects a leader. And when Raft elects a leader, it will inform our process to say, okay, I'm either becoming leader or I'm stepping down. And yeah, so it will basically communicate with the Raft process through its own leader election. So I think this not everybody sort of uses this. Like if in the Kubernetes example, sort of etcd is just the key value store. And then the sort of processes are accessing the store run on separate nodes. So it doesn't even need to know like the state of the consensus, like who's the leader and stuff like that. So that's sort of a more flexible approach. But yeah, since in Alexio, we already have this concept of leader. And the reason why we have the leader is because it's going to make sort of external state changes to the workers and the UFS. And it basically just simplifies our system to have a single primary master running at a time. And yeah, we sort of use the Raft mechanism as part of this.
Got it. So in one of your blog associated with this talk is something saying that Kafka actually the new design no longer using Zookeeper. Is that true? And I haven't really checked their designs.
Right. So I know I've read that Kafka is moving away from Zookeeper, but I think in that specific blog that I'm linking to is specific to Confluent. And so they're using their own implementation of their special implementation of Raft that sort of works especially for Kafka. And I'm not fully sure like how their system works, but yeah, I mean, at least in the Confluent, they're using Raft as the sort of coordination between the Kafka brokers.
I see. I see. So, but you're not talking about the Apache Kafka. You're talking about the Confluence Kafka.
Mhm.
Okay. So there is a, oh, somebody said it's in version 2.8. Maybe that's referring this.
Okay.
Ian and said it's version 2.8. Okay. So
Okay.
there's a few questions asked. I forgot his name, but is Raft open source?
So actually Raft it comes from an academic paper, and it's sort of what Raft is it's sort of a state machine replication algorithm, which is based on Paxos, and it's sort of like a simplified version. And then what happens is there's a bunch of different people who have implemented this Raft algorithm, and they're implemented in different languages. So we're, in the case of Alexio, we're using a Java version of Raft, which is, it's called Apache Radis. It's an Apache project.
Yeah, some
So I
people
see
ask,
this question. Sorry.
yeah, there's a question asking which library you use. So maybe you can select just put on the chat and see what's the project name, and so people can research on their own. Okay, another question is, just in general, say, what is the Raft's benefits and advantage over Zookeeper? Zookeeper has been widely used for most distributed system, example, in HDFS and Spark, Kafka, etc. Maybe he just asked you to summarize what's the key benefits.
Yeah, so yeah, that's interesting because at the core, Zookeeper and Raft are sort of almost like almost nearly identical consensus algorithms. But the main difference is that Raft, all that Raft is sort of just giving you this interface to build your own replicated state machine. So Raft gives this interface to a state machine, which you can provide any sort of state machine. So for Alexio, we're using this sort of key value store based on RocksDB. And then Zookeeper itself, I think the best way to think about it is that Zookeeper already implements a specific state machine, which is sort of this file system abstraction. And within that, it provides different services. So one of them is leader election, one of them is naming, and there's some other services. So I think for a lot of things, especially if it's for just coordination, Zookeeper itself is sufficient. But for us, like we wanted to sort of store large amounts of metadata, which didn't quite work with the Zookeeper abstraction. So with Raft, it allowed us to sort of implement our own sort of metadata key value store structure within the state machine. So I think there's a lot of similarities, but it's more sort of the thing, like if the Raft or if the Zookeeper sort of tools and abstractions already work for you, then would be sufficient.
Got it. So one question about the replacing your general logs with like a RockDB type of a key value pairs. The general log has the time essentially in better time. One is started first, second, third, like a second and third. So that's a sequence of the time. So if you're using key value pairs, did you lose the time as well?
Right. So what we're using the time for is like the log itself. We're purely using it for recovery. So with the log, we have this total order of events, and it's used for, in case of failure or a new node starting, it's going to take this log and execute them one at a time. And so what's nice about Raft is that it sort of takes care of all this for you. It chooses through its consensus, it gives a single order. And then when Raft will actually do the recovery for you. So since it's just these commands, since the log is just going to be these commands to the state machine, like the order itself is sort of abstracted away from us. We don't have to worry about it anymore. So Raft is just going to, start our key value store, and then apply the commands in the same order that they were executed or that they were decided on. So basically Raft is doing all this for us. We don't have to worry about it. Of course, like within our state machine, we can, if we want to store additional like timing data and stuff like that, we can. We just don't have to worry about the specifics of sort of replaying the log and recovering.
Okay, that's very nice. So any other questions? I've been asking a bunch of questions. Any other questions, please post it on the chat. Or if you would like to talk, you can just unmute yourself and ask question directly.
Yeah, and so I should also say, if you want more information on Alexio, you can visit the website, or it's also an open source project. So there's a GitHub and a Slack community.
Yeah, Alexio has been used quite a number of in production in quite a number of companies from both the US and China. So so it's any other questions? If not, so we would like to thank. Oh, somebody just posed a question. I'll just go back to say, okay. Terminology questions. Does Zookeeper provides a field system? What's that? System abstraction, or rather, our key value store. Oh, file
Yes.
system abstraction.
Yeah, so it's so Zookeeper. Its base is, it's a sort of a hierarchical file system with it has versioning numbers. And you can probably use that, implement a key value store from that. I think the abstraction is quite powerful. They give you, yes, some sort of a lot of different options, and like versioning, and I think synchronization through locking, and that can be implemented through leader election. So yeah, I think Zookeeper itself is quite powerful. In our case, we found the performance and the scalability was more applicable using sort of our sort of custom data storage on top of RocksDB. I think Zookeeper is all in memory too, so it didn't quite fit our needs.
Okay, I think that will be our last question. So I'd like to thank Tyler for gave the excellent talks. So thank you for joining for this meetup. The slides will be shared on the meetup page when getting Tyler can send to me, and the recording will be posted on the YouTube channels probably tomorrow or something like that. Okay, thank you all. We'll see you next time.
Great, thank you.
Bye-bye.